Hello. I'll be speaking about Fluence and TSS for the rescue of decentralization. So Fluence is a decentralized serverless compute platform. Basically, what does it mean? What does decentralized mean? It means distributed, trustless, unstoppable, fault-tolerant, and so on. It's a compute platform, which means that Fluence replicates, in a sense, the cloud stack, so that building decentralized applications from scratch becomes much more easy. And Fluence's objective is to enable running arbitrary code without limitations with a similar speed and utility as the cloud. So we want to run general purpose applications. And we want to run them anywhere, on the edge, locally, in the browser, on the backend. No consensus required, it's optional, and that means that we have a highly performant computation, which is quite cheap. It's asynchronous, so you can use parallelism on the network heavily. And it's compatible with multiple data I/O. You can read, write from different protocols, chains like IPFS, Filecoin, Arweave, L1, L2, and so on. And compute platform begins with the compute marketplace. So let's begin the Fluence overview with the Web3 compute marketplace. Fluence network runs on a decentralized compute marketplace so that anyone can contribute compute capacity, which means that it's an open protocol, and the open protocol eliminates switching costs between providers. And with no switching costs, there is a competition, and compute costs are driven down. And it allows de-risking the application, as there is no provider lock-in, there's no API to shut off, there's no means to censor data and to check what can or cannot run on the network. So the entry barriers to distributed or decentralized applications, or to create multi-party protocols and run them in the wild, reduced. What does the compute marketplace look like? We have the on-chain part, so compute marketplace runs on the chain. Currently, it's Filecoin. And we have the off-chain part, so the compute itself happens off-chain. We have compute providers. We expect them to run a lot of servers. Each server is represented in the marketplace with the offer, with some attributes for the compute jobs that can run on these servers, like the pricing and advanced capabilities. And developer can choose the pricing policy, what external I/O is required. Like if I need GPU, I will take providers given GPU. If I need calling HTTPS, I will ask provider to give this capability and so on. Then I can choose how many compute providers to take, how many peers to take from each of the providers. I can whitelist and blacklist providers for deal inclusion or exclusion. Finally, it looks like this. I have a deal transaction that I want to put my application on the network. It goes to the compute marketplace, and the matching happens. So some of the peers allocate the resources, here represented as workers, the gray workers on 3 of the peers. And these workers are registered into the on-chain deal, so we can find the part of the infrastructure that will be running our jobs, our application, our protocol on the network. If the peer goes down, then as all the criteria are kept on chain, the new peer will appear. That's why we call it a serverless platform, a decentralized serverless, because you don't need to care about particular servers. Once it's deployed, it forms a subnet, and let's speak a little about the subnets. So here we have those three peers with workers, so it's our part of the network. And it's a subnet, and subnet is constituted by the user code deployed on the workers on many peers, and this code consists of WebAssembly services running with the Marine runtime, and the multi-party flows between these all these peers, all these workers, and maybe the user running with Aqua. So we can have this Fluence stack comparison with the cloud. It's very, very rough. So for AWS Lambda, for local compute jobs, we have Marine. For step functions and distributed flows, we have Aqua. And for the emergent behaviors like load balancing, routing, scaling, orchestration, deploy, we have Aqua libraries. So all these behaviors are not the part of the protocol. They are scriptable, pluggable. They don't require recompiling or redeploying the network to be updated. So it's a very open infrastructure. A few words about Aqua. Aqua is a multi-party language that manages a distributed execution flow. And you can use Aqua to invoke subnet services and also to extend subnet functionality, to add consensus if needed, to do load balancing, replication, or to implement the multi-party part of multi-party computation. And here's a small snippet of what is possible with Aqua. Here we have a for cycle with a parallelism. We have types. Then after for with parallelism, it's actually fork pattern. When you fork the execution flow onto several peers. And then we have join. We can do timeouts, and so on. So it's quite powerful and very straightforward because it's a kind of a domain-specific language. And this Aqua acts as an ephemeral coordinator, or it forms a protocol fundamentally. Every execution is a kind of a protocol. There is no single party who runs this Aqua. It flows from peer to peer. So no single party. That's nice, and no blockchain involved on the same time. No blockchain, off-chain, very, very efficient, no blockchain. So fundamentally, Aqua language and Marine runtime serves as a tool set to make multi-party protocols. You do the compute part, the library code into the language that compiles to WebAssembly or that can run on WebAssembly. And you deploy, provision, maintain, update, redeploy, orchestrate with Aqua and Marine. MPC and like TSS is a very good example of what exactly can be coordinated this way. So let's take a look at MPC. For MPC, we collaborate with the Silence Labs. So I ask Sushi to describe.
Thanks, Dmitry. I feel short standing next to Dmitry. Anyways, hi, I'm Sushi. I'm a applied cryptographer at Silence Labs. I focus on writing the libraries and helping our clients use it in their solutions. So yeah, so I was unsure of the audience for this talk, so bear with me for a quick introduction to MPC. So MPC, we have multiple parties. They have secrets. They want to compute some function together over the data, and they want to give it private. That's it. That's my overview for MPC. And today, I want to talk about a subset of MPC, that is threshold signature schemes, and which usually comes with three functions that it supports. So first is distributed key generation, also known as DKG commonly, and distributed sign generation and key refresh. So using our rigorous math notation that we established earlier, so distributed key generation, the function that we're evaluating is key generation, just creating a new key. And the output is a share for each party. And the share can, depending on the protocol, can be additive or Shamir secret shares. So the private data that each party is providing to the protocol is just random data that they have sampled. So an interesting thing with MPC protocols, we have this notion of key refresh, where you can run a protocol to refresh or re-randomize your key shares. And yeah, that's the function that's being run for key refresh, and the input is the current key share that the party holds. And for distributed sign generation, we run any signing algorithm. And in this, commonly used is ECDSA and EDDSA. And it outputs a valid signature. And we give the key share that we have after DKG. OK, so I just want to show how it looks in practice. This is specific to a two-party case. And just a simple sequence diagram to showcase how the flow looks. It's just a very simple like ping pong messaging, where party 1 starts it off by creating a message 1, and party 2 processes it, and then they go back and forth for 2 rounds, and in the end you have a sign or a key share. This is just a rough overflow. It's not accurate with the rounds and everything. Just wanted to show it. Okay, so yeah, so this is just a code example I wanted to show a library and how easy it is to use. So I basically want to make MPC easy to use, and someone who they don't have to understand how it works entirely to use it. So this is just doing sign generation in 6 lines. It's all happening locally. Do not recommend doing this. But yeah, in a practical setting, the parties will be in hopefully very far away from each other. But yeah, this is how easy it is to do distributed sign generation. Okay, so state of threshold signatures as Silence Labs. We have our two-party library. It's written in Rust. We expose a C API, WASM API, a TypeScript package, or any other language you need. We'll get it done. And these are some numbers for keygen and sign. And for our multi-party library, we also have a Rust library. We expose all sorts of APIs and any other wrapper you require. And these are our initial preliminary benchmarks. And I'm very happy with these numbers. And we're already working on a bunch of optimizations. And I'm sure it'll get better with time. OK, so now what? We have a library. We make it easy to use. What do we do next? So now, when we come to the real setting, we have a lot of problems. Like, how do parties authenticate with each other? How is the communication done? Right? Like, so what are the guarantees of the communication layer? Where is compute done? Who hosts that, and how does that work? So we've been looking at alternate solutions for this for a few months now, and you'll see a bunch of talks later. And while doing research for this, we came across Fluence, and we were kind of interested in what they can do together with MPC. So yeah, so I think Dmitry will show you like what we were able to do with Fluence. Yeah, over to him.
Hello. Can we switch to Zoom? Wonderful. Yeah, it works. So let's discuss protocols on Aqua and take two-party TSS MPC as an example. So we are going to allocate 2 servers as 2 parties, or even better, we will allocate 4 servers to replicate each party's shares. We will have 2 copies on different peers. We already allocated workers on the network, so we have a subnet, and now we want to generate key shares, generate signature for an Ethereum address, and rotate the shares. So these steps will complete the TSS lifecycle. So let's begin with generating the key shares. Here's the sequence diagram of what's going to happen in the very first demo. It's almost the same that Sushi shown, but with this party of init peer, that's the CLI that I'm going to be running that just shows what's going to happen. And fundamentally, this is the Aqua code that I'm going to run, and this is the demo 1. I'm going to write something to the console locally. It happens locally. Then I run the keygen round trip function, and I'm going to use Fluence CLI for it. Fluence CLI handles all the setup for the Fluence application. So it connected to the peer, and it done the key generation. So let's take a look on the Aqua code that was executed. I need to command click. So we created the parties. We got the workers from the get workers helper, and then it's so straightforward. You see, I move the execution. The next block is going to be executed on the first worker. And this happens on the first worker. I get the variable from the keygen round 0. Then I print some blocks to the console. I do it in non-blocking fashion with co, which means coroutine. Then I go to the second party. I use the data from the first party. I do logs. I finalize the key generation for the first party. Here it is. I finalize key generation for the second party. Here it is. I do some assignments and like logs, these logs here. So it's extremely straightforward. It's the same sequence diagram, but following all the arrows. I'm just follow the arrows in a single script. It's not divided into different parties. I don't need to recompile it. It's a scripting language. It compiles on the fly. So I don't know a simpler way to do multi-party part of MPC, given the libraries provided. But actually, this makes a little sense because the key share is not persisted. I just show it in the console and then drop away. So let's switch to the second demo to have replication and persistence. It's just the demo 2. This is the demo 2. I'm going to set 2 shares among 4 peers, and it returns an Ethereum address. We can take a look on the code. So we collect different workers for different services. We deployed several subnets, fundamentally. We have a lot of workers. We use functions which form a MPC TSS library, which is also reusable. Then we get the Ethereum address, and we check that everything is okay with this fork join pattern. If it takes more than 5 seconds to complete, then it timeouts. So pretty nice. Now we have this Ethereum address created, and we have key shares of this Ethereum address persisted. So let's check that the shares for this address actually exist with a new call. We take the Ethereum address as an argument because our signing service implementation can store many shares for different addresses and create signatures for different addresses based on what you want. So it shows the shares in the console. Of course, it's made for demo purpose. You will not want to provide the shares in the open form through the API, but it's just to show that it actually works. It's super straightforward. So that was the keygen example. And we did the keygen, then we did keygen with persistence, and then we checked the key shares. Now let's make a signature. So in our setup, the services deployed on all the peers are the same, so they can play both roles. You have two-party TSS creation. They can be of the first role and on the second role, and we have a lot of small services on different subnets. You can make a fat service. You can make a lot of small services. They are very cheap in deployment. And Fluence supports all the approaches. So let's take a look on the signature creation. We have here the message to sign, the Ethereum address, and the derivation path. Let's use it. And hope that it will sign everything. So we have the signature here. We have some logs. It also works and is quite fast. So Aqua coordinates MPC signature creation as well. At this point, I want to take a side note on the protocol security. Just a few words. We have a lot of considerations on the security of the protocol and what exactly we provide with the protocol for the developers. But the baseline, we have end-to-end encryption on libp2p level. We use libp2p for networking. And the Aqua flow execution itself, as there's no coordinator, it means that execution is moved from peer to peer, and every next peer verifies all the previous steps of the flow. So if the flow is violated, then this violation can be proved on-chain. So the stake can be slashed, the stake of the peer, of the malicious peer, that changed the data or like removed the data from the previous steps or did something like that. For the peer level security, we have TEE in development. That means that right now the shares are stored in the open form in the file system, but we are working on TEE. And to provide resilience, you need to distribute work. If you have sensitive data, if you want not to lose it and so on, it's better to have a subnet. That's why the unit of deployment is a subnet, not just one peer, one service. And they should collaborate to provide the required service level. And for security inside the services, you can authenticate with a peer ID, you can authenticate with capabilities like Kakao or signatures, or you can use MPC signatures from other subnets so that one subnet can be authorized with MPC to trigger some execution on another subnet. So, okay, we have keygen, we have signature creation. Let's rotate the key shares and let's regenerate the key shares and ensure that the Ethereum address is the same, is the 5th demo. It will also locate all the peers, storing the shares, the signing workers, the keygen workers, and we'll take the key shares of signing workers to keygen refresh functions, and there are multiple rounds, many round trips between the parties, everything orchestrated with Aqua. So a lot of things happening here. We have Web3 utilities to generate Ethereum address back from the public key, and so on. A lot of things. All of them are reusable, and the Aqua flow itself is reusable. You can use it as library and like for other purposes. So that's pretty nice. And another nice thing is that for rotating the keys, right now I did press the enter button. Like I have this Fluence CLI, and I triggered the flow pushing the button. But you can do it automated way with spells. So Fluence has a concept of spells. Spells are Aqua functions running periodically on the workers. So they are like cron jobs with some additions. They are distributed multi-party cron because Aqua is distributed. They have a key value store to retain intermediary data to store it between the calls. And also spells execution can be triggered not just by the timer, but by blockchain events as well. And given that we have MPC on decentralized network in such a pluggable and composable, customizable way, what it enables. We can do a lot of multi-party algorithms the same way. And we can use many subnets of different behaviors, different capabilities in a single Aqua flow. For example, we can take Fluence RPC, which provides distributed access to blockchain data. That's another demo that we have. To read blockchain data, then we can deploy a subnet for data analysis that takes the data from RPCs and make some decision based on the on-chain events. And then we can sign a transaction with MPC and send it on-chain with proofs for the source data and for the decision being made by authorized parties, and do some composition like this, do some pipelines. So it could look like this when we have different subnets, and we can have blockchain on the left, blockchain on the right. It could be different blockchains. We can push execution to the web browser as well, as we can run Fluence Peer in the web browser. So that's quite powerful. And a few words about the next steps and where we are. We have developer experience flow and the compute providers flow. For the developer experience, we want to have two-party and n-party MPC available for all the Fluence subnets. That's currently, you need to speak to Silence Labs to get this demo working for you. And we want to speed up MPC and different cryptography solutions with the native JMP and crypto modules for WebAssembly. Right now, it's all happens in WebAssembly, which is quite slow. We can optimize. We want to have a very fine-grained encryption, peer-to-peer encryption on the level of services. We want to have a secret management SDK to prevent user errors which could lead to secret leaking. And we're working on TE for WebAssembly modules. But fundamentally, given that we can expect us to deliver all of this, all the toolset already works. We have the testnet deployed. We have several testnets. So you can develop things right away. And for the compute provider flow, I said that the servers could have some capacity, and you can get capacity. And for the decentralized network, for sure, we cannot just trust compute providers to provide the capacity. So we measure this capacity with a proof of capacity, which is a CPU and a RAM intense proof of work. So we focus on CPU mainly. And we provide incentives for compute providers to provide capacity to the Fluence network. So we are going to bootstrap the mainnet in Q4 with this proof of work for compute providers. And we are going to release proof processing, proof of Aqua execution, on-chain proof of Aqua execution in Q1 next year. So that was everything on my side. Thank you very much. See fluence.network for more. Join fluence.chat. It's our Discord, and ask me anything. I'm around on this event. Thank you.
Any questions? Those two demos, I saw a hand up there, one hand here.
I have so many questions because this is tightly related to my research. So first off, I'm curious about the TSS that you used and that you support. Is there a particular TSS algorithm that you support, and how did you choose that?
Oh yeah, we use Lindell 17 for two-party, and for multi-party we use DKLS.
So I'm very curious, with the Fluence network, if we're going to apply TKLS on top of Fluence, I mean, the whole point of a threshold signature scheme, any TSS, is that, you know, if you have corruptions or an adversary that takes over a part of the network, then you're fine. But if everything is going through Fluence, like even if you might have multiple parties underneath, if somebody were to either plant a backdoor or do something with the Fluence network, what prevents such an adversary from taking over more than your threshold of your workers and basically breaking the TSS scheme?
The point is that you can whitelist providers, and you can pick different providers, ensuring that there is no more than given number of servers from every provider. We incentivize economically providers to compose the proofs. So it's much more efficient if the proofs of capacity and proof processing are composed into a single proof before sending it on-chain. So probably, highly likely, from the economically perspective, it's very reasonable to have the real providers registered as distinct providers. So if the economical incentive is not enough for you to ensure the security, the replication between different data centers, if it's not enough for you, then you use whitelist to make sure that you know the providers where it will be distributed.
That's great for the providers, but if everything is flowing through Fluence, what prevents Fluence from acting as that malicious adversary?
What kind of Fluence? It's an open protocol.
It never runs through any, like Fluence is providing all of this as a marketplace, but does this data go through Fluence or no?
Marketplace is running on-chain, so it's decentralized, no Fluence in between. Fluence is a protocol. Fluence off-chain protocol has open incentives. It's an open protocol. Anyone can join, anyone can leave. It's governed on-chain, so no Fluence guys in between.
Thank you.
Hey, so I have a question. What does it take to integrate with Aqua? Like, if I want to bring on a new protocol, and how does it work technically? Is it based on JavaScript or? Two questions, I guess.
Yeah. So, what it takes to integrate? You can try out one of our quick starts, but you will end up with something like this. You install Fluence CLI, you do Fluence init, and then you have Aqua folder and services folder, and in the services folder, by default, you have Rust code. And if you have a library that could be compiled to WebAssembly, C, NIM, Rust, something like this, you need to provide a facade to it and do something like this. When you have a module that does just like definition of the public interface and that ensures some business invariants, business rules, like here we have the marine macro that helps with everything. So for compute, if you want compute to be portable, and probably you want it to be portable so that it's safe and nice for compute providers to run it without knowing who you are and so on, then you need to compile it to WebAssembly. And it's quite straightforward. We implement WebAssembly interface types specification. Our services could consist of many modules, so you can reuse modules, you can reuse services as whole, and so on. So after you have this, you have the generated Aqua types for it. Here, this is auto-generated. You have the service name, you have all the functions, all the types. And you can write...
the Rust bindings, or auto-generated from what?
From the type definitions of Rust from this marine macro.
I see, I see.
But it's not very custom. This marine macro creates interface types section in the WebAssembly file, and then we fetch the definitions from WebAssembly interface types. And we have this, and after that you can just create an Aqua file. Probably you want to do Fluence dep install for some libraries that we provide or something else. And then you just begin writing. If you want to have some output, you could just return. We have an Aqua book with documentation. You can learn it while you're coding and playing with all of this. For the logs, you can, like right now, it runs. It comes with the bundled-in Docker Compose file that runs the local network. and you can, if you use Docker desktop, you can see the logs and see what's happening to debug. So everything is here.
Cool. Yeah. Thanks.
Yeah, so I have a question. So breach of privacy is not detectable, right? In Fluence. So for example, if I have my private key in the servers and they somehow reconstruct it and use it in some other system, then you cannot hold them accountable because it is basically also indistinguishable from the case where I am actually trying to frame you leaking my private key.
So the question is, how could we prevent leaking of the private key or of the shares, right?
Yeah, yeah.
Yeah, that's why I had this slide on the very end about very fine-grained encryption on the protocol level, and where it was here. So this is about three things fundamentally. The first thing is how exactly can I transfer the secret, any kind of secret, from one peer to another peer, given that Aqua works in such a way that it needs an access to the data to do routing. So all the data by default is transparent to all the peers on the flow. You need to explicitly hide the secrets, and we're working on an end-to-end encryption scheme that comes from one service to another service. Then the next question is how exactly the secret is stored and managed and used on the peer. We're working on secret management SDK. But finally, the decryption of peer-to-peer encrypted message of the secret should happen only inside TEE. And there is a TEE solution for WebAssembly modules that we're integrating. So finally, there will be no possibility for the secret leaking because it will come to TEE and it will not be revealed in any form to the peer. But today, you need to have some level of trust while developing the solution before we come to mainnet and before we have all of this implemented. Does it answer your question?
Yeah, so my second question was that now suppose I also have the secret key, right? And the secret key is also stored in your network. So if there is a message that is signed with the secret key, how do you distinguish that it is me who is signing or the network is maliciously signing?
Okay, and for that, yeah, Sushi can.
So the user does not have a key here. It's more of like a federated type of model. So that's also back to your original question. It's a valid question, right? We thought about it. I think we were just discussing it yesterday. So we are already not, the user does not have a key share. We are already trusting that this network, will at least have one honest party or majority honest parties. So yeah, but we can try our best to make it difficult, but this is like a inherent drawback of user not having the keys.
Thanks.
And I would like to add a few words. So I'm from Fluence, Fluence Labs, like protocol for compute. And I'm speaking about Aqua language and Marine runtime as a tool set to make multi-party protocols. So I don't speak that we have solved all the security issues. We provide the tooling for the guys like you who can use it either to do bad things or good things. But we're just the infrastructure. You can run
good things
on the infrastructure.
Questions? No? Thank you. Thank you so much for your time, both of you.